Hi, Professor Shanlu and all other students. I am Yuanjian, and I'm currently in Hangzhou, which is a beautiful city in China, and you are all welcome to travel here after the pandemic. Because of the time difference and efficiency of conveying information in 10 minutes, I edited together a video to better introduce what I did in the course project. The main contribution we made is the implementation of an improved lossy compression algorithm, which follows the basic workflow of SD2, but we wrote most of the SD2 code in C++17 and separate each stage to better support the switches of different algorithms. The compression algorithm can be used to transfer some huge simulated scientific data, as the compression ratio can be much higher than the lossless compression. Even with such higher compression ratios, the error band is preserved so that we take much less network traffic, but the decompressed data are usable for analysis. Sydney and I wanted to build a website that integrates all parts of our programs, including compression, transfer, visualization, and so on, to give users a better interface. But later, we found that no matter how fancy the website we build, it cannot be written into the paper. Damn. From the research perspective, the evaluation graphs will be sufficient. So, without further ado, let's introduce the main designs and evaluation results. First of all, the compression can be separated into 4 stages: prediction, quantization, Huffman encoding, and lossless compression. To clarify, the algorithm is prediction-based, which means we use neighboring data to predict a data value for a specific data point. It's already described in previous papers. We can see in there. We can use the 3 red points to predict this data point. If the prediction is accurate, we can save the space for that data point. That's exactly how the prediction will do the compression work and decrease the file size. However, normally, data cannot be accurately predicted by nearby data points. But the hypothesis is the data have some sort of locality so that nearby data are close to each other, or at least in some similar data ranges. Under this assumption, we apply a quantization method. The quantization method is also described in previous papers. For example, this is the global range quantization method. First, we have a prediction value, and the prediction value is not accurate enough since it's quite far from the real value. The quantization is basically to move it back to the point that is within the error band to the real value. In our implementation, the quantization part is more complicated than this, because we need to support multi-ranges and different error bands. To preserve multiple error bands, the hard part is to make sure the decompressed data in the decompression stage are identical to the corresponding data in the compression stage. We designed 2 dedicated algorithms to handle this. The first is this one, and it deals with the compression stage, and the second deals with the decompression stage. Because of the multi-ranges, there are some edge cases that require special care when the data is close to the range boundary. For example, in A's case, the decompressed data goes beyond the range boundary, and we must pull it back. We can pull it back here, or we can pull it back here. If we always pull it back to the 1 error band position, then lots of data points that are close to the range boundary will gather together on this point. However, according to users' demand and our evaluation, there will be many data points that are so close to the boundary that they should be treated as the boundary. Since users might set a rather high error band, then the distortion will be huge if we pull it back to this position. Another thing to mention is that we discovered that many datasets contain some irrelevant data, which might represent the coastline or something that is not relevant to the data we care. For example, we care about water level or temperature or wind speed, but some irrelevant data mix among the normal data points. They will break the data locality and cause the data points to be unpredictable, and thus reduce the compression ratio. We use the Lorenzo predictor to handle this irrelevant data by replacing them with the Lorenzo predicted result. In this way, the locality is preserved and we can have higher compression ratio. Okay, let's briefly describe our evaluation results. We use 5 datasets as shown here to do the evaluation. 4 of them are in binary format and 1 is in HDF5 format. We have to write an HDF5 filter and integrate it into our program to handle Hurricane Katrina datasets. But as HDF5 is quite common format in scientific data, especially in those supercomputer-related simulation results, we believe our implementation is helpful for future research. We visualize a slice of 33120, that many of data, we just visualize 1 to show that our results with double range and will be much better than the original SD2's result. If we set the error bound to be 0.5, we can see that there are so many artifacts, but by setting 2 range correctly, we can reach a much higher compression ratio, and the graph is basically identical, almost identical to the original data. If the SZ wants to reach the compression ratio of 60, like it's just a 59, we need to set the error bound to be 0.8, and there will be much more artifacts. Another dataset we would like to show is the Miranda density. This is the density of some datasets, and actually you can see that when we set triple range, the compression ratio is 109. There will be much fewer artifacts than the original method. And if we set double range and allow the compression ratio to decrease a bit, but it's still higher than the original results, we can see there will be almost no artifacts. These are the 2 graphs that easily show that our algorithm is somewhat better than the original one. Due to the time limit, let's quickly look at the irrelevant data handling algorithm. We can see in the Hurricane Isabella dataset, the irrelevant data only takes a tiny portion, but it indeed breaks the locality of data. We can see it here. The data is separated 2 parts. We use 120 to represent the irrelevant data. After clearing it with the Lorenzo predictor, we can see the locality is preserved. And the compression ratio is also higher, though not a lot, because irrelevant data only takes such a small portion in this dataset. Finally, combining the multi-range quantization, different prediction algorithms, and the irrelevant data handling, we can see that our algorithms have much higher compression ratio than the fallback version, which means SD2. And we can see from the visualization, the shapes of the hurricane generated by our algorithm is better than the fallback version. Okay, that's about the paper. We also implemented a demo to use Globus, transfer, and FuncX to actually compress and transfer the data between 2 or more endpoints. I used the 2 computers to do the experiment. One is my 13-inch MacBook Pro and the other is my 16-inch MacBook Pro. The compression and the visualization programs can definitely be deployed to all sorts of Linux machines. Thanks for listening. This is Yuanjian and my presentation for the course project CMSC 331 Advanced Operating System. If you like the content, please subscribe to the channel for more awesomeness and see you next time.